Uni-modal embeddings take some form of inputs like text, images, audio, and convert them into a vector. And that is stuff we are used to the most and that most applications use nowadays. They, for example, only work on text to text. Multimodal embeddings learn a joint embedding space. So you can actually search images with text. The assumption is that they can learn a richer representation of the world. So if we take, for example, text to image embedding models like Clip, they can learn concepts that are very hard to be put into words or are impossible to be put into words. But we can go even further. So for example, LiDAR, radar, ultrasonic. We could even add modalities we as humans cannot process. We can also add human behaviors, events, emotions, or humor and try to embed those. But how do we actually train such models? I think only a few people have even fine-tuned multimodal embedding models. Few have trained them from scratch because that's mostly reserved for the big labs. And today we are trying to answer exactly that. We are continuing our series on embeddings and on search. So welcome back to How AI is Built. Today we are talking to Michael Günther, who is a machine learning scientist at JINA AI, working on multimodal embeddings. And we will be especially looking at JINA Clip, a model that has broken most of the benchmarks when it comes to text-to-image embedding models when it came out. And we will be talking about how they trained it, how they constructed a data set, how you can construct a data set for your specific use case, and how you can use it to fine-tune your own models. But we will also be talking about the applications of it. So how it is already used in production, or what use cases they have seen that work very well.
Re-rankers are mostly used for text embeddings, right? So they're not so much like for clip-like models. Re-rankers are not so common. But yeah, for text embedding models, for text retrieval models, it's really like that on one hand, the re-rankers are having much better accuracy. So basically you put in like the query and the document. So that gives the model a much better way to find a good retrieval score. And it's easier to adjust the relevancy based on the query. So that makes it also working much better for out-of-distribution, because embedding models are generally working much worse on out-of-distribution tasks than re-rankers. Yeah. The only thing which helps with embeddings to get better on out-of-distribution tasks are instruction-based embeddings, of course. But this doesn't get as close as re-rankers can work on out-of-distribution.
Yeah, what do you mean exactly by instruction-based embeddings?
So instruction-based embeddings are basically embeddings which are trained in a way that you add for each text value you want to embed a prefix, like a prompt in a large language model, which describes what is the task it should be embedded for. For example, for retrieval, it's of course a difference if you have a task which is a question answering task, so the model should find the answer to the question, or if it's for example, a duplicate detection task where the task is, it should embed it so that it's similar to a duplicate. And then you have also like typical benchmarks, for example, for fact checking, where you basically have a fact given, and then you want to redrive evidences for the fact, which are the fact is true, but also you want to redrive things which are completely negation of the fact, which to basically falsify that the fact is true. Yeah. And it's all kind of different objectives which
we will ever hit the universal embedding, so one embedding model to rule them all?
Yeah, I think one thing is that, as I said, you have like very different objectives. And yeah, probably it would have been a model where you can really precisely describe what you actually want the embedding model to before. And then also one problem is if you're in a company and you have very specific data and the embedding model hasn't seen anything like that before, then probably it will also not be perfect. Even for large language models, they are universal, but still people fine-tuning them on domain-specific data if they want to employ them on a very specific use case in their company.
Yeah. Maybe connected to that, because I see already, especially for smaller companies, but also for startups, many of those are not doing like the traditional AI or ML, where they actually think about the architecture, set up an entire model, train it on a task, investigate it, but rather do the pre-trained model and fine-tune it on the task paradigm. Do you actually expect that engineers in the future will still train entire models from scratch? Or do you expect that for like most tasks that are out there, we will have a few pre-trained models and it's just like more efficient in terms of performance and also compute to just take them and fine-tune them?
Yeah, I think for generally pre-training allows the model to basically learn concepts which are very general and probably can be transferred for many tasks. So I think there are lots of applications where pre-training actually helps, and also for embedding models, you can see that definitely if you fine-tune in a pre-trained embedding model, which is already contrastively trained to produce good embeddings, it will perform much better than if you just try to train a model, an embedding model from scratch, even from a pre-trained transformer model, if your data collection isn't massive. And however, there are also still, of course, applications where you can see either for example, you have text which is not really natural language, then probably taking a pre-trained model doesn't help you in any sense. And also, of course, there are some applications where you could use an existing pre-trained big model and fine-tune it, but you need more efficiency. So maybe it's better to basically train a very small, I don't know, random forest classifier or whatever. Or even for embedding models, there are probably some techniques which are much more efficient to generate embeddings. Maybe for your application that makes more sense to have a very small model you can run on a CPU and do lots of inferences in a very short time.
Yeah. Do you still, in your research, try out different architectures, for example, LSTMs, RNNs, or CNNs for generating embeddings as well and training them on a specific task?
Yeah, actually, we're doing relatively applied research, I would say.
Yeah.
And it's always risky, and probably in most cases you're not very successful if you try to invent everything from scratch. Yeah. So what we usually do is we try to see what is already working and try to do more smaller modifications where we think that we have a relatively high probability on succeed with this. We're not. I think if you're doing research in academia, it's a bit easier to try out something completely new. And
yeah. What would you say, like on a conceptual level, what's the main difference, especially between the multimodal and the single modal embedding models?
Yeah, the obvious difference is, of course, the single model can only accept one type of modality as input, and the multimodal can accept multiple types. And then on most of the models, they have somehow component which can, of course, since the input modality is different fundamentally, for example, images are fundamentally different. To process then text, you need a specific way to transform it into an input you can give into a neural network. So, for example, vision transformers, they take the image features and then they put it into split one image into multiple small image patches, which they can process. While for text models, you have a tokenizer which tokenizes the text sequence and then basically map each of the tokens to a specific input embedding representation. So those are different techniques, and then you usually have an encoder component for each modality. However, in particular, how the inputs are combined by a model can be very different depending on the type of multi-modal model.
Can you double click on that? Or what are the different ways you could combine the different modalities?
Yeah, so for text image models, there are basically, I would say, 3 rough types. Probably you can find more, but which I most commonly see. One is this, I would say, clip-like models, where you basically have a vision transformer model and a text transformer model. Text transformer model is responsible for encoding the text, and the vision transformer model is responsible for encoding the image. And then both have some projection layer where they map the output on a shared vector space, or basically mapping it into embedding of the same dimensionality. And those are basically two independent towers, which, however, are trained simultaneously to basically map an image which is related to a text value on similar embedding representations. And then I think other way are vision language models. For example, there is this Pali-Gemma model, which also has been used for recent co-Pali model, and they basically, it's a vision language model where you first have also a vision transformer model. A vision transformer, as I said, a bit usually splits the images into image patches and then process as tokens like the transformer model for text, and then it generates for each patch basically one patch embedding at the end, and those patch embeddings are basically used then by another transformer model in a way that these more like similar to text transformer model gets first as a prefix all the embeddings of the image patches, then getting some prefix text, and can then basically further generate text based on it. And the co-Pali model, basically what they have invented is that they take such a kind of model, taking in the embeddings of the image patches, pass it through a transformer model, and then you're getting multiple embeddings for each of the vision patches. And then you have a Colbert type retrieval matching, where you basically have a query, which is also tokenized into embeddings. And then you matching each of these token embeddings to each of the image patches and determine the maximum similarity and average these maximum similarities to get a final similarity score. And this is specifically good for more complex document matching. Yeah, okay, this was a bit long about the vision language models, and I think a third type is also that you just have basically some kind of vision encoder and a text encoder, which producing embeddings for image patches and for tokens. And then you have another transformer component, which gets both as inputs and produces an output. Maybe an interesting model recently came out, which is using this architecture, is the Magic Lens model from Google. And what they basically doing is that they wanted to have a model for image-to-image matching. But if you do image-to-image matching, it's often not so clearly defined what is the objective here, as we said that instructions for text embedding models are used to basically define a retrieval objective. So they also wanted to have this for images, that you say you have an image and then you say, I don't want to have just the image which is somehow similar, but I want to have something which shows the same thing as a sketch or something like this. And then we can take these instructions and the image and encode it into a joint representation.
Yeah, and especially from an applied side, how do you actually decide like which of these three types might be most suitable? Are there like some heuristics, or from your experience, like some guides which you can give, or do you in the end always have to end up testing the different options?
Yeah, one thing you can definitely look is if you have the papers available or some documentation about the model, look at what kind of benchmarks they're evaluating on. And then you can basically look what benchmarks is most similar to my problem. And then you can take a model which performs good on this benchmark. And this is I think, general recommendation. If you don't have a benchmark which is somehow similar to your problem, then of course you can also take a look at the architecture and say, okay, maybe if I just have a generic text to image search problem, maybe I just use a normal clip model. But if I have something more complex, then maybe I use a model with a different architecture which can better model this problem.
When I have a retrieval task, what is especially the trade-off in terms of performance whether I just use multiple single modality embedding models and run multiple retrieval systems at the same time and then re-rank, versus using one joint model with a joint embedding space or whatever for retrieval. Are there any research papers that come to mind that actually try to compare those?
I don't know. I haven't seen too much research papers comparing this, or at least I have no in mind. But yeah, so the case you're asking is you have a text query and you want to have search for some item which has an image and a text property, right?
Yeah.
Yeah, something like this. So what you can do is you can basically just either basically use a text embedding model and an image embedding model, and a text to image embedding model, and then basically using the text embedding to redrive similar embeddings of just the text, and then using basically like model to redrive for the text similar images, and then somehow combine the result sets. Or you can what you can use with your clip-like model, for example, you can use the text encoder and the image encoder of the clip embedding to produce two embeddings of the image part and the text part of an item and average them. That can also work decently good, especially with this JINA Clip model, which we have trained to produce high quality text embeddings also, and which can also be used for text-to-text retrieval. There we have seen that on some product search tests that actually using the average embeddings works quite good. However, for example, one common problem is that you might have some items which only have a text property or only have an image property, or one of them is very low quality and you cannot use. And then one problem you observe is that the scale of the similarity values, which you redrive from an item which has only a text or which has only an image, is very different from a scale from an averaged embedding, if you combine an average embedding from this. So in those cases, I think then sometimes using like just two embeddings which just capture a single modality are probably a better choice.
Yeah. And what is, especially when I'm looking at new modalities, I think like the image bind paper, for example, included depth as one separate modality. I think like the first question for me would be like, what makes a modality? And then how can I, based on the modalities I include, how can I actually figure out how to best combine the modalities I'm adding to the model?
Yeah, I think what's made up of modalities, it's maybe just already a bit philosophical question, I don't know. But so if you want to add a new modality to a model, so I think one simple way you could do is that maybe if you have some model already which can translate from one modality into another, for example, if you have some audio sequence and you can just use something like Whisper or so to convert it into text and then use a text transformer, maybe this already will work, right? But might not work if you have some audio which is not really speech or something like that, for example. So that could be a simple option. I would sometimes just maybe first try out before training your own new model. And another thing is that if you want to add a new modality into a model, then I think one very difficult aspect is always to then find sufficiently good training data you can actually use to train these models. So you need probably some data sets which relates the two modalities in a way that it captures the notion of similarity you want to capture. And having those kind of data in a sufficiently big amount. And then you probably, if you design a model, you then have to come up with what is a good method to encode these data into a representation which can be processed by neural networks efficiently, and so on.
So basically, first challenge would be to figure out a representation or train a model to represent the new modality. The second would be then to basically figure out a way or create a data set that can bring the new modality and the existing modalities into a joint embedding space so I can actually calculate the similarity between them. Can you maybe, by the example of JINA Clip, give us an example of how the process actually looks like for creating a data set for training a multimodal model, and what especially also the different fields in a data set are?
Yeah, what we used to train JINA Clip was, of course, we utilize a lot of already existing data sets. There's this Lion 400 million and Lion 5B data set, which is basically widely used to train clip models, and we just reuse this data. Then we also, our focus was to create a model which is better for text-to-text search, rely on our collection of text training data we have from our JINA text embedding models. And basically, this was a relatively long process to collect those data sets. Basically, we just tried to get a very diverse set of pairs of texts from different domains so that the model is very general. We also did a lot of filtering. For example, we filter out duplicate text pairs. We filter out things which are not from, for example, if you want to train an English model, then we don't want to have data from other languages. And yeah, we also did some more filtering methods like consistency filtering, where you basically take an existing embedding model and try to filter out text pairs where the text is unrelated. Similar for the Lion dataset, for example, they also, to construct it, used an existing clip model and tried to filter out all the, basically Lion consists of images and their captions, so that you basically can train a clip model to encode text and a caption and the image into a similar embedding representation, and basically try to train the model so that it encodes the captions of a different image into a dissimilar representation. And yeah, they also used a clip model to basically check whether the text value is actually related to the image, and if it's below a threshold, then they filter it out. So that's a kind of filtering they do. Yeah, for the JINA Clip model, we noticed that basically should I get already into the training or?
Yeah.
Okay, so the training is basically, maybe to have a short background story. So what we actually thought first we could do is to basically take an encoder of our JINA text embedding models and try to adjust existing vision transformers by continued training to encode the images into some embeddings as the text based on an image captioning dataset. And thereby we wanted to keep the text encoder freezed so that we don't change anything on the text encoder, and the model is also then compatible with our existing JINA text embedding models. However, it turns out this was actually not working at all. And we later also found out that there are actually some papers which show that if you freeze a text encoder, basically you cannot efficiently train a clip model. And so, and basically then we thought, okay, we try to train the model more without freezing anything. So we train also the text encoder part. And here we thought, okay, we basically utilize a kind of multitask training method. So basically train the model on pairs of texts and images, as clip is usually trained together. So training on both objectives at the same time. And this was working quite well, but we also realized that the model has not as good text capabilities. And we found out that this was actually the case because the image captions you usually train a model on, they are very short. So they are not the model cannot learn too much from the image captions. So basically we needed some data set which has longer captions and more descriptive descriptions of the actual images. So, and then we basically found an existing data set which has syntactic descriptions of images, which are partly generated by a large language model and partly by image captioning model, which is then trained on these synthetic data. So that was basically how we collected the data for training.
And did you also compare it to a triplet loss, where you actually also have negative examples for the images or the text in the end?
Yeah, good question. So the actual training, so for text models, they are usually trained in 2 stages. So after the normal pre-training of the text transformer model, you usually train on text pairs, which you can easily get in a very large amount. So you can easily get 1 billion pairs or something like that. And then basically train it in a contrastive way, so that the model is trained to encode 2 text values which are part of a pair to be similar. And from the text pairs which are also inside the batch, you then take all the right side of the pairs which are not part of your pair and say the similarity score should be low 2. And usually after that, you train text embedding models on more smaller high quality data sets where you actually have, for example, for retrieval data sets, some queries and the specific relevant document, and also annotated some documents which are not relevant to this text value. And then you can use them as additional negatives in your loss. And you can also, if your high quality data set doesn't have annotated negatives, you can also mine them by, for example, taking an embedding model, look what an existing embedding model gives you for relevant text values, which might not actually be relevant because the re-ranker model ranks them lower. And doing the training of our JINA Clip model, we also wanted to do the same to improve the text retrieval capabilities of this model. So we basically ended up with 3 stages. The first stage, we basically train our text model on image captions and images on one hand and on text pairs on the other hand. In the second stage, we continue to training on these text pairs, but include longer image captions from another data set, plus the actual images. And in the third stage, we continue training on long captions and images. And for the text part, we actually then train the model on our triplet data sets where we basically have these additional hard negatives.
Yeah. And especially on the evaluation side, I want to especially know, like, when you're looking at the paper and you're looking at a new model or a new find an existing model, what are you first looking at when you try to assess it, or what are the different things you look at in like evaluations, in the methodologies to actually assess the quality?
Yeah, so I think, you're looking, of course, on the benchmarks and how it compares to other models, but also what you think should take a look on is, of course, how the models are trained. Is it data which is related to this task? And the performance of the model might then come from basically that they use training data which is specific for this task. So they might have then a better score on the specific benchmark for this. But also, if you basically want to use a model or something like that, or compared to a model, then also makes sense to, of course, choose a model where the training data has been similar to what you actually want to use it for. Yeah.
And especially looking at your training process, why didn't you fine-tune the image embedder as well with pairs of images?
Embedder was, I think, we in the model, basically, I think our model is not specifically trained for image-to-image search, I would say.
Yeah.
Otherwise, maybe we would have done this. But yeah, maybe it would be an interesting idea to also do this and see if then you can get a model which is better for image search.
Yeah. So it likely would be that if I create like an additional data set and continue the pre-training of the image embedder, that I would likely have like better performance on like image-to-image search as well.
Yeah, it could be. Yeah.
Can it be that this might interfere, or the different types of searches? So when I'm basically trying to specialize the model on like text-to-image search, I'm better off doing your process. And when I try to specialize on like image to text, image to image search, I'm better off doing the other process, and they're interfering with each other if I try to do both.
Yeah, I think in general it's always if you fine tune a model, it's very likely that it's using its generalizability properties a bit, so it might generalize then less good on other tasks, of course, that you probably have to be aware of. So I guess, when you train the model then only on image-to-image pairs, then it might lose its text-to-image capabilities.
Yeah, and we're looking more at like how to maybe take your model and basically adopt it to a new task. So if I, for example, had an e-commerce setting and I want to adapt the model to actually be more suited to especially the query types you often have on e-commerce sites, which is usually like very like shorter queries with only a few words, how would you actually go about creating a data set to fine-tune JINA Clip for the specific task?
Yeah, in the ideal case, you of course have some, if you are an e-commerce company, you maybe have some click data, you maybe have some query log also you could use, and then basically try to relate the queries directly to descriptions of the images and descriptions of the products you have. If you don't have this, or not in large amounts, or you don't want to use it because it's your customer data, and you don't want to train on it, then what you can also do is to take a specific model to basically which can generate captions generate queries for your products. For example, if you have some good product descriptions, maybe you can just use a large language model to produce some queries about these documents. And then you can use this as a data set for you. There's also like a method which is called generative pseudo-labeling. And this is they actually have done this previously with a very simple model, which is trained to generate questions. And then they have used it only for text retrieval purpose, but basically they take the document collection, constructing questions about these documents, and then they could show when fine-tuning on this data, then the model performs much better on the existing document collection. So I think you can probably do this for your e-commerce application as well.
Yeah, so like I'm pulling up the research paper right now. So what it basically does, you generate synthetic queries for the passages in the target domain. So you basically try to do it. I think that's really interesting, especially if you also add the paper on getting 1 billion personas from the internet. So basically create user personas and then use that on top to basically create like different types of queries. This could be really interesting and also speed up a dataset creation greatly. Nice. And in this case, would you actually only fine-tune the text embedder, or would you basically fine-tune the entire model?
That's a good question. I think I would, or rather, like, I can imagine that having a training process which resembles the last stage of our training more closely probably leads to better results if you basically use the model for text-to-text and text-to-image retrieval together, and then just training the text encoder, because then, maybe the model does a bit connection to the image modality.
Yeah, and also would save you a lot of work. Nice. What do you think are like for JINA Clip? What are some of the like interesting or also weird use cases you have seen so far, or that you have tested them internally?
Yeah, we don't have talked with, as the model is relatively new, we haven't talked too much with users, but one application which actually often comes out is actually e-commerce, or like product recommendation and search, because this is also a domain where you can really see that you have a lot of data on the internet which is about products, for example. And accordingly, the model is trained on similar data, and therefore it performs good and probably much better than on a domain where you cannot find much data on the internet. And as I said, did a small experiment where I tried out this averaging, where I tried to average the description of a product and the image of the embedding of the description of a product and embedding of the image of the product, and the resulting representation was actually quite good. But that's also interesting that this works well. However, as I said, it also has some limitations, especially if you some product missing a description or image.
Yeah. What would you say, like, people or other engineers actually can take away? Because most of them won't train their own embedding model or even go through such a large scale training process. What are like the main learnings you would give to other engineers that don't go like through the massive experience you have?
I think, one thing is, definitely to be aware of the scale of similarity values you have. So I think one often misconception we had also for the text models was actually that the similarity values might not reflect the typical similarity, a notion of similarity you have in mind. For example, many text embedding models, they have produce always very high similarity values, even though they are not, the two text values are not similar at all. But if you compare then the similarity values to other similarity values of text which you have embedded together, then it makes more sense. I think that's important also, that the similarity values between embeddings of images and embeddings of text and images and text are on a very different scale. And so that's important to consider. Another thing is always when you try to optimize some model, I think what is definitely important is to have some kind of a way to quantitatively evaluate on how good is the model before your optimization and afterwards. I think that's definitely something you should do before you start a lot of effort to optimize something. And I think if you consider fine-tuning, I think what's some general hints would also be that often for training embedding models and also for fine-tuning, large batch sizes are actually important. And in order to produce large batch sizes, you also have to enable some performance optimizations. For example, our JINA Clip model has flash attention support. So you can use this to reduce the memory the model consumes during training on the GPU. And also you can use activation checkpointing, which saves you a lot of memory. And then maybe also one thing is also be aware maybe of the limitations of the model. For example, if you use a vision model or a multi-modal model which can get images, you have to be aware what is the resolution the model scales the images down. And if your images are very big and you want to recognize something which is very small on the images, then the model might not be able to solve your task because of this downscaling of the resolution. And in a similar way, if you have very long texts, but before you encode them, you truncate them into very small chunks, then into very small parts, then of course maybe the information you want to search for is not encoded at all. So that maybe some hints.
Especially like the scale of similarities, is there a type of distribution you're looking for typically? Like you're looking for a normal distribution or anything? Or are you rather looking for, is it a power law to one of the extremes?
It's very, so as the one thing you notice is that many embedding models, specifically text embedding models, are trained in a way that they map all the text values on a cone in the vector space. And if you then calculate the cosine similarity, then they have all a very high cosine similarity. But it seems like for some tasks, the models then perform better if the embeddings are all on this cone. And it's easier for the model to model a certain type of similar model, some contrastive objective, when this is the case. But I think some people of course are a bit confused that all the similarity values are above 0.5 or so. If you take a E5 model, for example.
In the end, makes like thresholds less usable when you have like a distribution that biases to the higher side. Nice. What would you actually say is missing from the space?
I think one thing which might be missing is maybe that there are, especially for multi-modal tasks and these complex retrieval tasks, is a bit that there are not so many benchmarks you can actually use. For example, we try to find benchmarks for a search type where you have a text and then you have like products of text and images, and you find some things in the e-commerce space, which you can more or less use as benchmarks, like there's a data set which contains products from Amazon and very fine granular category descriptions you can use as queries maybe. But in general, I think it would be very nice if there would be a bit more benchmarks and also like people which maybe use these models that they can, and they notice that something is not working perfectly, that they can maybe try to create a small data sets where people can evaluate and researchers can try to find models which can work good on these tasks. So I think that would be something very useful. Yeah, and also I think there are, especially also in the last months, came out a lot of vision language models and embedding models which support multiple modalities. It would be very interesting to see what kind of applications you can solve with all these models. That are here.
Nice. What's next, especially like for JINA? What's on the horizon? You can already tease or what are you working on?
So we actually working on a new version of our JINA Clip model, which supports more languages. So at the moment, the JINA Clip model only supports English, which is, of course, big limitation, and trying to make that. And then in our team, what we're also working on is a new version of our text embedding model. So if you look at slides, you can see that the JINA text embeddings, they are far apart from all the other models meanwhile. And will soon probably publish a new model, which is also multilingual and has better performance. And then what we want to probably focus on further is to actually look into more complex multi-modal search applications and also try to build models for this. Nice. Maybe also take a look at Copali and its capabilities and limitations and see what's actually what this model is maybe not so good at and what we can contribute there.
What is one more underappreciated or niche technology that you think deserves more attention?
One thing which has been done quite some research, but I haven't seen it so popular and also not many people putting it into products is encoding of more semi-structured data and more data with a bit more structure, so tables, maybe also some models which can code things, multi-modal data, which is in some structure. So I think that would be definitely the direction that would be interesting. And then maybe what would be also interesting is that actually some people which said that they want to use clip models for tasks where you have images which are not like typical photos, but more on images of data from different things, for example, from like some plants or some images which represent some other type of image data. And I think that maybe would also be interesting to see how actually clip models perform in these different kinds of images and what can be done to improve the performance on those domains.
Nice. And if people want to follow along with JINA, where can they do that?
Yeah, of course, we have on our website a blog where we always publish some, I think, probably interesting articles about some new things in the space of search with AI models. Our models are published on Hugging Face page. We, of course, also have these search foundations where you have different API-based products to build your search applications. And also you can, multiple of me and my colleagues are active on Twitter or LinkedIn and posting something from time to time.
So what can we take away? I think, first of all, his thoughts on the universal embedding model are spot on. I think also that we are unlikely to have a universal embedding model in the terms of high performance. I think we will hit a universal embedding model which is good enough for a lot of tasks, which some people might argue we have right now with, for example, OpenAI's embeddings, but I would say it isn't really, because if you try it for search it works quite well. But if you go beyond that, for example, for anomaly detection or recommendations, it won't work well. I think for a universal embedding model or a model to qualify as universal, I would like that it has like a baseline of performance that qualifies it as like good enough for many different use cases. So I can basically build a prototype around it. But I think universal embedding models, in terms like we will see outperformance or performance on par with the state of the art, I don't expect that we will see it anytime soon. So I think the objectives and domain specific needs are so different that you will always be better off training your own model and constructing your own data sets, and also trying to get more efficient, because performance is one thing in terms of like for example, accuracy, but performance in terms of speed or throughput is another. And universal embedding models are likely very large, which make them unsuitable for a lot of applications. I think the types of text to image models are like the three main types, like clip-like models with two different encoders, which are then joined at the end into a joint embedding space, vision language models, which basically prefix an image before they start to generate text, and then hybrid models, which I'm not exactly sure on the like what then is a hybrid model, what's the clear definition. I think he mentioned the magic lens model is a good example for that. I have to read into it, but that they basically allow for more complex interactions between the modality. So I think it's basically separate encoders, but with additional transformer components integrated. But yeah, I think like the three different types are very interesting. And also as guidance, like what embedding model to use. Look into the paper, look into what benchmarks they have run, but maybe also look into like what is the lab researching. Especially if it's an industrial lab, you might find an industrial lab which put out a benchmark which is working in an area that's actually very close to yours or on a use case that's close to yours. So try to find an embedding model which either outperforms on the benchmark, if the benchmark is similar to your task, or industry lab which is working in a space that's very similar to yours. And also evaluate the architecture based on the task complexity. I think the most interesting insight I would highlight is that freezing the text encoder can hinder the clip model training. And I would love to know why, but I think like if you go into training a clip model, this is something to remember. And also, it already highlights the original clip model, like the training data they used, which is very short captions, highlights like how important it is to look into the research paper and also look into the data sets they used, whether they actually mirror the data you will be seeing. Because if you have very long captions or descriptions by users, you're unlikely to perform well with a clip model out of the box because the data is so different and it's basically out of domain. And another one is basically large batch sizes, that you should train embedding models on a large batch size. Yes, I think that's it for me for the main takeaways. I thought it was really interesting. If you have any questions on multimodal embedding models or would like to see some fine-tuning scripts, I'm working on a few right now. Just let me know in the comments or give me a ping on LinkedIn. Otherwise, we will be continuing more on embeddings next week. So subscribe, like it, and let me know what you think. See you next week.